Now we start the theory of the course, and I start with section 1.1 and example 1.1.1. The numbering that I use here in the slides is the numbering that I also use in the book. So this is also example 1.1.1 in the book. In this example, imagine that you are a street vendor and you have to decide one time, only tomorrow, what to do. You can have a little booth at the beach of the North Sea, and you have to decide which merchandise to take along with you. On other days, there's a other street vendor there, so you can't be only tomorrow. It's a one-time decision. You have to decide whether you take along with you ice cream, hot dogs, neither, or both. That's your decision. And the only thing you care about is how much money you make tomorrow, but that depends on the weather condition tomorrow. So let me set up a table, how this works. There can be no rain, some rain, or all rain tomorrow. Now, for instance, if you do ice cream and no rain, then you make quite a bit of money. You make 400 euro. Some rain, then you make less, only 100 euro. All rain, then in fact you lose because you don't sell much. But ice cream, you can't keep it. It gets spoiled. You can't take it back tomorrow. So then you lose 400. Maybe you see I'm using the weather condition as discrete events. Maybe you think it's more realistic to take a continuum to say the percentage of time that it will rain tomorrow, and maybe also how much it will rain and other weather conditions. But let's assume that for simplicity that this analysis is refined enough to give the right definition. So for simplicity, we just assume 3 discrete events and that's it. Now for hot dogs, if there is no rain, you don't sell much. And hot dogs also, you can't keep them, they get spoiled. So then you lose 400 euro. Some rain, then you gain 100 euro. But all rain, well, there may not be many people, but they like hot dogs much. Then you gain 400 euro from having hot dogs. Neither is, of course, 0. If you take both along with you, then I assume that we can just add the profits you make. So then in no rain, it's 400 minus 400 is 0. Some rain, it's 200. All rain, it's again 0. So I do assume that there is no interaction between the different merchandises. So how many hot dogs you sell does not depend on whether or not you take ice cream along with you and vice versa. No interaction between merchandises. I'm introducing some notation. X denotes ice cream. Y denotes hot dogs, 0 neither, X plus Y denotes both. And X plus Y, then by definition, it means that for every event, you just add the separate outcomes, the profits you make. And if this merchandises were to interact with each other, then maybe some other merchandise would give this exactly the sum of these payoffs. But we keep it simple in this example. So let's just assume that X plus Y is both merchandise, no interaction, just to have a simple example. Some further notation. Event S1 is the event of no rain. The event of some rain I denote S2. The event of all rain I denote S3. Now this letter S is the abbreviating state of nature. That's a bit of a weird term, but it's the term that people use in the literature, so we do it also, state of nature. But often I would just say event. These are events, they may happen, you're not sure if they happen, you're uncertain about it. But formally we denote them S1, S2, S3. Now, this example is a bit of a childish example. It's a toy example. I use it to illustrate all kind of didactical things in this course. But briefly, I'll mention a more realistic version of a similar example, such as the situation happened in finance. And in fact, this first meeting is dealing with the arbitrage idea of finance, the center idea of finance. That will come later. For now, the more realistic example, imagine you can trade on the financial market. So you have to do a deposit and things like that. But imagine you can trade on the financial market. You're going to speculate on copper price next month. Now, K abbreviates thousands, and I put up in one blow the whole table with all the payoffs, and I will explain them. In X means you speculate on a high copper price, and if the price is above this threshold, you gain 50K. If it's below the threshold, you lose 30K. And Y is the opposite. Y, you speculate on a low copper price. If it's below the threshold, you gain 50K. In the other case, you lose 50K. Let's assume that. Maybe you find it a bit strange again that we have these discrete events. Maybe you think it would be more natural if your profits would depend in a continuous manner on the copper price next month. But maybe people with finance training, they know that really such financial position exists. In the finance market, every assignment of payment to every event is available as a financial position that you can buy or sell. So indeed, such discrete financial positions are conceivable. If the price is 1 cent below 2.53, with actually already lose 30K. If it's 1 cent above, you gain 50K. This is possible. So this is realistic in this example. If you do neither of these positions 0, and if you do both, you get the sum of these payoffs. So then here I summed all the events. So these kind of decision situations happen a lot in finance. They have the same structure as the street vendor example, but they are more serious maybe. But for didactical reasons, I will continue this course using the toy example of the street vendor. So let us discuss that a bit more. I put up the payoff matrix and we're going to discuss it. I'm going to ask you now, imagine so that you are the street vendor. What would you do in this situation? How would you go about making your decision? Now, you can pause the video and think for a while. And then when you made up your mind what you do, how you handle this, you come back. Okay, I assume you made up your mind, you come back. And then one thing that people often say in this situation, often what they do is they say, I'm going to look at expected value. Let me take probabilities 1/3, 1/3, 1/3 when doing that. Then the expected value of X is 1/3 times 400 plus 1/3 times 100 plus 1/3 times minus 400. And then you get 33.3. For Y, you do similar calculation. Again, the expected value is 33.3. 0, of course, 0. X plus Y is 1/3 times 200 is 66.6. So if you do that, then X plus Y, taking both, has the highest expected value, and that is what you do. But I assume that many listeners immediately noticed a very weak point in what I did. I was just assuming these probabilities 1/3, 1/3 for no good reason. Why would these events be equally likely in terms of probability? That need not at all be the case. If you look at maybe when you're listening what the weather condition is and how it will be tomorrow in the beach in the North Sea, then maybe it can be that no rain is much more likely than some rain, and that all rain is very unlikely, or other things. It depends on the weather conditions, but not at all these events need to be equally likely. So if you want to do expected value in a bit of a more better way, then you have to find the good probabilities, really good, based on good much information maybe. So what you may do, maybe you collect all kind of statistics from internet. You get all the weather condition in Holland on that day of the year for the last few centuries. And then maybe you derive objective probabilities from that. Then you have good solid probabilities, and expected value makes more sense. But this is a bit more difficult than maybe first seems, because one problem is that tomorrow is not a random average day from the past few centuries, but tomorrow is one unique day that may, for instance, the weather conditions now may be different than they were ever in the past. Also, maybe climate change mean that the future will be a bit different than the past. So there are all kinds of reasons why it may not be so hard to get, not so easy to get such objective probabilities. And some people even argue they don't exist, they are not meaningful in such unique event situations. So that's already a bit problematic. And even if in principle it were possible, and maybe you don't have much time, you have to very quickly decide with whatever information you have now, you have to decide already what you do, then you just don't have the time to find those statistics. So therefore, these probabilities, objective probabilities, are often hard to find. Another problem with expected value is even if you have good objective probabilities, many people don't like that formula of expected value so much. They rather bring a risk aversion or look at variance or things like that. So that's another reason why people question this approach. So expected value maximization is very debatable, to say the least. In fact, that will be the main topic of this whole meeting. But many people also, when they look at this table, they don't think very much about expected value, but they say, you know what, that X plus Y option looks quite nice. You never lose and you can gain some. Of course, 0 is not good. Nobody will consider the 0 option because X plus Y is superior to 0, but X plus Y is quite nice. So many people, for that reason, just say, I'm going for X plus Y. However, that can still not be so. For instance, if you are in a situation where no rain is quite likely to occur, and all rain is very unlikely, and maybe some rain is also unlikely, in such a situation, maybe still you really want to go for the ice cream, not for both. So it's anyway, it's not very easy how to decide. An expected value is interesting but debatable, and the rest of this meeting we'll discuss that in much more detail. But now I want to introduce some notation, some formal notation to prepare for the things that we're going to do the rest of this meeting. First, I'm going to introduce a notation with tuples of numbers. Here's an element from R3, so tuple of real numbers. This is a merchandise where you gain x1 euro for event S1 no rain, x2 euro for event S2 some rain, x3 euro for event S3 all rain. So this specifies simply for every event how much money you make. We are assuming that the only thing that you care about is how much money you make. So then this notation can be convenient and good for your purposes. For instance, if ice cream is then the tuple 400, 100, minus 400. Later today in this meeting, we will also consider many other tuples of numbers. And for instance, we will maybe sometimes we consider the tuple 20 million, 7 million, 11 million. And then you may say, now what kind of merchandise could ever give such profits? There would be a sort of miracle merchandise. But indeed, we will be looking at many types of numbers, and some are very hypothetical, but still we consider them all to be a part of our domain of preference. And then, sometimes it can be good. Very hypothetical things can still help to clarify this situation, clarify thinking. That's surely the case here. So later in this meeting, we'll be looking at all kinds of types of numbers and things about it. But for now, let us stick with this example. Let's assume for simplicity that only these 4 options are available, and you have to choose from them. Now I'm going to define expected value maximization. I wrote it as a proposal here, but the formally expected value maximization means that you get some probability, you choose determined probabilities of the events, where P1 is your subjective probability of event S1, P2 is the event for S2, and P3 for S3. Probabilities are non-negative, they add to 1, right? So they satisfy that. And of course, we already discussed that it can be very problematic. But anyway, with expected value model, we assume that one way or the other you have to get them best way that you can to do expected value maximization. Then after that, you can imagine how it goes. Then when you have to choose between different options, you choose the one with the highest expected value. Let us look at an example. Let's assume that you, after good thinking, you came out that you think, I think the probability of no rain tomorrow is 0.4, and the probability of some rain and all rain tomorrow, they are both 0.3. Maybe these are good, wise probabilities or whatever that you are using. Then if we do the expected value calculation, then we get the expected value of ice cream is 0.4 times 400 plus 0.3 times 100 plus 0.3 times minus 400, and we calculate it is 70. We do the same for hot dogs, and I immediately wrote here the result. We do the calculation, we find it's minus 10, the expected value. 0, of course, is 0. The expected value of x plus y is 0.3 times 200, and that is 60. Maybe you also know the expected value of the sum is the sum of the expected values, and you know it must be 70 plus minus 10, so 60. But anyway, 60 it is. From these calculations, you see that ice cream X has the highest expected value. So that is what you do. That is what you choose. And in particular, in this example, the probability of no rain is high enough, and the probability of all rain, also some rain, are small enough that ice cream is worthwhile. It is better than doing both in this example. Anyway, this is how it works, but of course, there's much to be discussed and much controversial about it, and that we will discuss at great length in the rest of this meeting, but that will be continued in the next recordings.